recording. Okay, so thank you all for joining the seminar. So today's speaker is Professor Juan Pablo Yanez. He got a PhD in experimental physics at the Humboldt University in Berlin, studying atmospheric neutrino oscillation with IceCube. He then got a different postdoc position, one at Daisy Zeuthen, still working on the neutrino oscillation and sterile neutrino searches. And then at the University of Alberta as a Banting Fellow, joining as No+, focusing on improving detector modeling in simulation towards the scintillator phase. And then since 2018, he is assistant professor at the University of Alberta, continues the involvement in IceCube and SNO+, and exploring the possibility of a large-scale neutrino detector in the Pacific Ocean P1. So now I leave Juan Pablo to start his talk. So thank you very much for being here, and go ahead. Thanks.
All right, thank you. I hope you can hear me okay. So it is really a pleasure to come here and talk to you about a topic that I find extremely interesting, which is neutrino oscillations and how you can do that with detectors that were really not meant to measure this kind of physics. I'm going to be focusing on IceCube, and towards the end, I'm going to discuss other exciting possibilities, particularly for those of us that are in Canada. So let me then start on how to measure neutrino oscillations with IceCube. We've been in the business of oscillations since 2013. First, I want to give you a really brief summary of why I find oscillations interesting. And I think a lot of people agree that this is an exciting topic. Neutrinos have an interesting place in the standard model. You have this nice display from Symmetry magazine that shows you the particles that form the standard model. You have the matter particles towards the outside of it, and you have the neutrinos here on this corner. There's a family of three. They are very light, but they are not massless, unlike, for example, the photon. So it makes it interesting. Also, they are only weakly interacting, and they happen to be very abundant. So they're really hard to measure because they're only weakly interacting, but they are very abundant. So you have a detector that is going to measure neutrinos, then you can have a lot of sources of neutrinos. They are detected and produced in weak interactions in vertices that look like this. This is, for example, an exchange of a charged boson where you had in your initial state a charged lepton, then you exchange a charged boson, and you have in your final state a neutrino. And these neutrinos are produced as flavor eigenstates. And depending on the charged lepton that you have here on the left is the flavor that you will assign to the neutrino state that you have on your right. Now, because they are produced as flavor eigenstate, you cannot really assign masses directly to the flavor states. You have to take the most general possibility in which there are some mass states that have well-defined masses, and there's some connection between those mass states and the flavor eigenstates. And the relationship between these two is encoded in a 3x3 matrix if you have three families, three neutrinos, and you can express it maybe more easily in this way. So if you have only three neutrinos and you respect unitarity, because why would you violate number of particles, then this matrix is going to be unitary and it's going to have 9 elements. You produce your neutrinos as flavor eigenstates, then they propagate as mass eigenstates, and when they interact again as flavor eigenstates, because they only interact via the weak interaction, and their eigenstate for the weak interaction is flavor. So if flavor eigenstates and mass eigenstates are not strictly the same, then you can have this phenomenon in which the neutrinos produce in one basis, it propagates in a different one, and then when it interacts, it doesn't have to interact in the same one. So you get neutrino mixing. Now, the standard model gives you the structure of the matrix that controls this mixing. So the standard model tells you something about this matrix here on the top. And this is one way to parameterize it. In general, you're going to end up with 3 real parameters, and those are the mixing angles. That's going to tell us the degree which neutrinos mix with one another. There will be 1 imaginary phase and 2 Majorana-only imaginary phases. Now, again, this is only one way of parameterizing this matrix in which you have factorized the different parameters to have their own little submatrix, which makes it very convenient, but there's nothing special about this way of factorizing the matrix. It's just convenient. And that lets us separate the Majorana phases here on the right, which, depending on your point of view, sadly or luckily, they are not relevant for oscillation experiments. So oscillations cannot tell you anything about the Majorana phases. Once you compute oscillation probabilities, these terms drop out, so it doesn't matter what they are. So I'm not going to be discussing that at all because we don't have a way to access them. Now, while the standard model gives you the matrix structure, it has nothing to say about the actual values that go into that matrix. You need to find out what these values are by experiment. And we do this by looking at the propagation neutrinos, and I'm going to here give first the example of vacuum. The amplitude for propagating some neutrino at a given time, and then detecting that with some flavor beta can be given by this expression. If you assume 2 neutrinos for simplicity and try your pencil to do the math, you end up with an oscillation probability that looks like this, which is very straightforward. You have an amplitude. You have only one mixing angle because we have assumed only 2 neutrinos for simplicity. And you have a phase here on the right. That phase depends on the difference of masses squared of those mass eigenstates, and the distance between the neutrino production and detection plays a role, as well as the energy of the neutrino. So the physics parameters that we want to extract are the mixing angles and the mass splitting, the mass differences, and the parameters that we can play with when we build an experiment are going to be the L, the distance between the production point and the detection point, and the energy. Now, this formula is very simple. It's only for 2 neutrinos. However, it just happens to be that it is a very good approximation when, if you have 3 neutrinos, if you have one mass splitting being much larger than the other one, then to first order, you can study a lot of the data in this way, and it can be useful in understanding some of the large effects that you expect when you build an experiment. Now, nobody does analysis using this simple formula anymore. We use the full formalism with 3 neutrinos, and we include matter effects, but this is just a good way to understand it. As I was saying, the mass difference inside. Now, one interesting caveat here is that the mass difference here is inside an even function. So the sign of that mass difference doesn't tell, is not something that you can access with vacuum oscillations. If you include matter, things get a little bit more complicated because you have to consider that neutrinos can scatter with ordinary matter. They can undergo charge current or neutral current interactions. If you don't go into anything exotic and you only take the neutrinos that we know of, they all interact via the neutral current in the exact same way. So you can forget about that because that's a global effect that affects all neutrinos equally. So the only one that matter will be the charge current interaction, and that will only affect electron neutrinos. If you consider the case of constant electron density, you can recycle the same formalism, and you end up with, again, in the case of 2 neutrinos, you can use the same formulas for the probabilities if you redefine your mixing angle and your mass splitting, and you redefine these parameters, introducing a new value that depends on the electron density and the energy of the neutrinos. And while this looks a little bit complicated, there's something interesting that comes out of this, is that because this term sits in the denominator here of the tangent, it really doesn't matter what value that angle has to begin with, this mixing angle. If you have the right conditions of energy and electron density, you can take a very small mixing angle and blow it up, because once this term over here tends to 1, then you have the tangent that tends towards infinity. So that would give you actually a mixing angle that is going to be close to the maximal value. So even in the case that you expect small oscillations, because the amplitude can be really small, the mixing angle can be really small, with the right conditions, you can make those oscillations really strong. So you can find resonance conditions. And this will be something that I will touch on towards the end when I show one of the results that we have right now. So the current knowledge on this mixing matrix comes for this first submatrix mainly from experiments looking at atmospheric neutrinos and long baseline accelerators, where you have a facility that produces neutrinos and then you have hundreds of kilometers away a detector. The parameters in the matrix in the middle come mainly from reactor neutrinos, and the ones on the right come mainly from solar neutrinos, a little bit of reactors as well. Most of these measurements are done in disappearance mode, meaning you start with some neutrinos of a given flavor, and then you see that you're lacking some later on in a detector that is downstream of where the flow was originated. Appearance experiments are usually tough because of many reasons, because the threshold set by the masses of your leptons, because of the design of the experiment. If you're going to detect a different channel, you have to design your experiment in a slightly different way. So they're tough, but they help in complementing the picture, in particular those from the first submatrix, the atmospheric ones that I'm going to discuss later. So this is the current knowledge of the mixing matrix that tells us how these mass states relate to these flavor eigenstates. And what I'm showing here is the 3 sigma regions for each one of the elements of the matrix. And what you can see is none of them are anywhere near 0. So there's some that are on the order of 0.1, but all of them seem to be pretty large. So there's a large degree of mixing between flavor and mass eigenstates. Just to give you a reference, this is the only other place in the standard model where such a similar-ish mixing takes place, which is in the quark sector. Now, the interesting thing, if you look at the CKA matrix of how quarks mix, is that these parameters in the diagonal, these elements, are really close to 1, and there's very little mixing in the off-diagonal elements. While in the neutrino sector, it doesn't seem to be the case. It seems like there is as much mixing as one can have. It seems to be that the randomness of this matrix is kind of maximized. So it's close to the maximal mixing possible, which has created a lot of interest from the theoretical side, because there could be a hint to another symmetry here. However, in order to do this, you would need much better precision. You can compare with the precision of the CKA matrix. It's really different to what we have on neutrinos now. Another thing that we don't know of the neutrinos is the mass ordering. We don't know which one is the lightest state. We have labeled neutrinos as M1, M2, and M3, or nu1, nu2, and nu3. We know that nu2 is larger than nu1 from SNO results, but we don't know if the third mass eigenstate is the heaviest or is the lightest. And another thing that we don't know, even though there are some hints, but it's not yet conclusive, is whether there is CP violation in the neutrino sector, whether neutrinos oscillate in a different way than antineutrinos, which is allowed by this phase that appeared in the submatrix that I had in the middle. Now, there's also interesting possibilities to go beyond standard oscillations, because if you had more neutrino states, looking at oscillations with high precision could be a way to show evidence for that. And you can do that by checking if all the measurements agree, or trying to make experiments that target some observed discrepancies. And you can do this also by focusing more on the appearance of the neutrinos, right? So up until now, most experiments look at this appearance, but you have to check what has happened with those neutrinos that went away. I mean, that was one of the really nice breakthroughs from SNO, that it could see that all the neutral currents were there and the electron neutrinos were disappearing. So anything that gives us an unexpected flavor composition is interesting, because it can point at some deficiencies in the theory that we have to explain that. So let me now move on to how we detect neutrinos on IceCube. I hope you believe me now that oscillations are interesting. Now let me show you how we detect neutrino interactions in IceCube. The detector is situated in Antarctica, right at the geographic South Pole. in one of the best places that you can go to get awesome auroras. And we're in Canada, but still, I think the South Pole, it's a good rival for that. IceCube is the largest neutrino detector in the world. It consists of 1 cubic kilometer of natural glacier ice that is monitored by over 5,000 photosensors. And we do this deep in the Antarctic ice. There is over 1.5 kilometers overburden from where the first sensors begin, and then the ice is instrumented down to a depth of 2.5 kilometers. Each of those 5,000 sensors looks like this. It's a 10-inch photomultiplier tube enclosed in a glass sphere with all the electronics for communication and readout enclosed together with the PMT. And using these PMTs, we can detect light using two modes. We have a high resolution mode in which we take time windows of 400 nanoseconds, 300 megasamples per second, which gives us the possibility of seeing really the waveform of the light. And we have another way to look for very elongated signals that looks with a much slower sampling rate of 40 megasamples per second, but we can look at a much longer time window at a time. So we detect the time at which light arrives, and we detect the amplitude, the charge that we have observed, so the number of photons that we have observed. The spacing in the detector is fairly large. So depending on which direction you look at, if it's vertical direction, 17 meter spacing. If it's horizontal plane, is about 125 meters. So there's a big distance between the sensors. And the DeepCore subarray, the sensors are a little bit closer together with a vertical distance of 7 meters and the horizontal plane distance of 40 to 70 meters. And this is going to set the energy threshold of the detector. We're only going to be sensitive to high energy neutrino interactions, starting at about 5 GeV, depending on the region. This region that can see the lowest energy neutrino interactions, that's DeepCore, which I'm highlighting here. It's on a shade of green, but in case you cannot see it, that's that region enclosed in red. Now, just to give you a little bit of a context of the size of the volume that DeepCore monitors, this is Super Kamiokande, one of the most iconic experiments in neutrino physics and atmospheric neutrinos. If you were to take Super Kamiokande, you could stack a few of them, actually 8 Super Kamiokandes, one on top of each other in the DeepCore volume. So the volume is huge, but is very sparsely instrumented because Super Kamiokande, for example, has twice the number of PMTs that IceCube has in the entire volume. So we have to rely on seeing only very high energy neutrino interactions. When we go to these very high energies, mostly what we're going to see is going to be deep inelastic scattering. And I'm talking over 90%, depending on the energy that you look at, it's going to be mostly deep inelastic scattering, where your interaction is a neutrino comes in, it interacts directly with one of the quarks in your nucleons in the water, in the ice, and you obtain either a charged lepton or a neutrino in the final state, depending on what kind of interaction. And you have disturbed the nucleon, so you start a shower of particles. These hadrons and electrons and most taus that are produced in this part over here are going to produce particle showers. They're going to be fairly localized for the scale of the detector. They develop over a scale of meters, and you saw the spacing is bigger than that. While muons and some extremely high energy taus have the possibility of making very long range tracks, which would fall over here. So that would leave a very distinct signature in your detector. The detection is done via Cherenkov light. That's why we need this large natural transparent medium. And that's why we go deep underground, so that it is as quiet as possible. This is an example of the light that is emitted by a muon track that is very high energy. And this is only a fraction of all the photons. This is from simulation, obviously, only a fraction of all the photons that would be produced as the muon track goes by. The range of muons at the energies that we're looking at can go from 10 meters to a few kilometers. So they can cross the entire detector and leave a very nice path as they go, which in an actual detector view would look like this, where each one of those blobs that are colored are a DOM, this digital optical module with a PMD inside that has seen some light. The color just tells you whether it's early or late, and the size is proportional to the number of photons that the DOM has seen. So when I say tracks, this is what these events look like. Now, if you don't have a long track, but you have a very highly energetic cascade, then this is how the light from this cascade looks like. The particles, they don't really travel that long, the charged particles that are producing the light, but the ice is very clear, so the light can travel hundreds of meters before it starts attenuating. So even though the particles develop over a short distance, they can light up a large fraction of the detector. And this is how one of these very high energy cascades would look like in IceCube. So this is how the events look like, but what is our main source of events? Well, our main source is due to cosmic rays, because cosmic rays interact in the atmosphere and they start these big showers, and one of the components of the showers, the meson component, produces muons and produces neutrinos, and that's going to be the main source of events for IceCube. The muons are by far the largest source of events from cosmic ray showers that are directly above the detector. Muons at very high energies can go all the way down into the ice, and we will see those. And currently the rate is about 2 kilohertz just from these muons. I'm not going to be discussing any studies with these muons. I'm going to be discussing studies with neutrinos. So that's obviously the other thing that we detect. Neutrinos we detect from all directions, though, because the Earth is mostly opaque is mostly transparent to neutrinos, unless you go to very high energies, but I'm not going to go there. So you can see neutrinos starting at a few GeV from all directions. And the ones that I'm going to be discussing for most of this presentation are atmospheric neutrinos, which are produced, again, by these cosmic ray showers, the same ones that make our biggest background. And you see here a plot that shows you the flux multiplied times the energy to the cube of the neutrinos expected at the South Pole. Mostly we see muon neutrinos in the energy range of interest, which starts somewhere here, a few GeV, down to the highest energies, 110, 100 TeV. And the flux is actually dropping very rapidly. That's why you need such a large detector to see it. Here it looks relatively flat just because there's an energy cube factor in there. So I'm going to be discussing mostly these atmospheric neutrinos that, as you can see, it's mostly muon neutrinos and antineutrinos. So how do we use these neutrinos to measure oscillations? So let me show you this very busy plot, but I think it's interesting. So I'm going to spend just a minute explaining what we have here. Here at the bottom, I have placed again the formula for oscillations that can be used for guiding our understanding of what we should do to measure these parameters. As I said, there are these L and E parameters that we can play with. So we can plot here in GeV scale at the bottom energies that we can access, and we can plot on the y-axis different distances that we can access. And I'm not going to talk about the amplitude right now. I just want to talk about this factor right here that tells you about the phase. So you see the mass splitting, the difference in masses between the neutrinos, is the one that multiplies this L over E factor. And we know of two mass splittings because we have 3 neutrinos. One is much larger than the other one. So there's really only 2 mass splittings that play a role at any given time. So what you can ask yourself is, for these energies and these different lengths at which you could build experiments to detect neutrinos on Earth, what is the highest energy at which you would expect to see the full effect of oscillations? And asking for the highest energy, because that would be generally the easiest that you can measure at the highest neutrino energies. And this is what this dashed line tells you here as it crosses this plot. If you follow that line, what that means is we have maximum effect from oscillations, meaning maximum transition from one flavor into another flavor. And if you want to test that effect, this is for one of the mass splittings, this is for the other mass splitting. So let's focus on the atmospheric one, this one on here. If you want to test that, I mean, we already know where this line is with some uncertainty. If you want to test that in more detail, then you need to build experiments at some L and E that are crossing that line. So these experiments that I'm showing here, for example, T2K, Dune, Nova, they are experiments meant to measure oscillations. They have a fixed baseline, but they have a wide range of energies, well, relatively wide range of energies at which they make measurements, right? But they have a fixed baseline. Now, the interesting thing about doing this with atmospheric neutrinos in a detector like IceCube is that you don't probe this line at a single point, but you really probe this line at a very large region where you expect oscillation effects, but you can also probe all outside the region just to see if there's anything else that we have not found out yet. So we're going to do both things. We do probing of known effects, and we do searches for oscillation-like effects in regions where we don't expect anything to happen. Now, the main effect that we expect to see, the known oscillations in DeepCore, in this more densely instrumented area of IceCube, is the disappearance of muoneutrinos. Here you have the survival probabilities of electrons and muoneutrinos, energy in the x-axis, cosine of zenith. On the y-axis, -1 means these neutrinos have crossed all of the Earth. 0 means they come from the horizon. You don't really see a lot of interesting features on the electron neutrino disappearance. You mostly get all of the electron neutrinos that you start with. But on the muoneutrino channel, there is this band over here where you expect close to maximal disappearance of your muoneutrinos. So we expect a really, really strong effect at energies of like 25 GeV. Now, these neutrinos that disappear mostly go to tau neutrinos, so we can also search for that. And another thing that you can get from this picture is that there's really no reason for oscillations past 100 GeV. And you could also have seen it in this plot here. So once you reach about 100 GeV, there should be no oscillations, at least none that we know of. So this is what we're looking for. We're looking for, on the low energies, this known pattern. And at the higher energies, we're looking for any pattern that would show an oscillation-like distortion in the spectrum of atmospheric neutrinos. The low energy analysis relies on using the inner volume as your fiducial volume, the DeepCore subdetector, and vetoing everything that seems to leave a signal outside of it. So we want to aggressively reject muons, and we also look only for starting events. So from these two pictures on the right, a muon would typically leave some signature as it comes in. So we don't want those kind of events. A neutrino that starts in the detector would leave no trace. Then there's an interaction in the detector, and then particles come out of that interaction vertex. So we keep those types of neutrinos. This event selection is a little more complicated than how I made it sound. It's a mix of straight cuts and BDTs, and we try to verify data Monte Carlo agreement all across the development of the selection, because the ice is a very complicated medium, so we have to deal with that. Once we have a sample of events that seem to start in the detector, we run a fairly expensive likelihood reconstruction where we fit all of the parameters that would describe an interaction, allowing for a potential muon track coming out of it and a hadronic shower. And we reach a 25% energy resolution for these type of events and about a 10-degree resolution in the direction. Now, those numbers are very different if you compare with, for example, beam experiments. So we're going to rely on the fact that we get thousands of these events, even though the event-by-event resolutions are not that great. On the high energy side, the story is a little bit different, because now the events leave very many hits in the detector. So you can rely on your reconstruction being really good and just look at those events that seem to come from underneath, because we know that neutrinos and muons both could produce this if the neutrino interacted somewhere before the detector, but it would be really hard to figure out a way to disentangle those, so we just throw them away. If we look only at events that are coming from below the horizon, kind of going up into the detector, only neutrinos can produce those, so we keep those. Again, this is a selection that is made with a mix of straight cuts and BDTs, and the likelihood fit's a little bit different because the event does not start inside the detector, but because these tracks leave a very long trail of light as they cross the detector, you actually reach a much better energy resolution of about 1 degree. So once we have our samples, we do the analysis by trying to parameterize our systematic effects. What do I mean by that? We're going to do a fit in a bin, either likelihood or chi-square space in multiple dimensions. In 3D is, for example, the one low energies. So we ask ourselves, what happens if we divide the cascade and the track channel as a function of reconstructed energy and reconstructed CNIT, and we start varying the mass splitting by some 1 sigma value of the expected uncertainty. You can see that on the cascade channel, you don't see a lot of effects, but on the track channel, there's a very sharp effect happening at some energies, because what you're doing when you modify the M squared is that you're shifting where the minimum is in your space of energy and cosine CNIT. These are the same variables that I showed for the disappearance probability earlier. So you have your minimum here, and you start moving it sideways. That's why you expect this very large percent change of up to 10%, but very localized. While if you modify some parameter that affects all of the detector, for example, the optical efficiency that we know to some extent, then you would actually expect a percent change in your number of events that is very much distributed all across, because if you have some parameter that affects all of the detector, then all of your events are going to be affected. While if you have a parameter that depends on physics that is related to some energies, only so those events are going to be affected. So all of this information goes into the experiment to fit systematic effects together with the physics parameters, and that's how we try to extract the most out of having so many events and try to be cautious with our sources of systematic errors. So we do the analysis in a blind fashion. We tune our Monte Carlo we tune our selection to Monte Carlo, and we track the agreement with data. And then what we do towards the end is that we run a fit where we look at all of the values, but we actually blind our oscillation parameters, and we only move forward if we have obtained a reasonable goodness of fit between data and simulation, and we usually put the threshold at about 5%. So if simulation agrees with data and get a p-value of 5% or better, then we think that our simulation is a good description of our detector, and we're going to believe the results that we get out of that. Now let me show you some of these results now that you know some of the gory details of how we do the analysis. On the low energy side, we have these 2 samples that I'm labeling here, A and B, and both of them have a lot of events. The latest published result that we have was 3 years, and we have in these samples between 60,000 and 41,000 neutrino events. And this is one display of these events for sample A in this L over E distribution. Towards the low L over E, there's no oscillation effects. Towards the right, there's oscillation effects. And you can even see these effects by eye, because look at how nice and smooth the distribution is on the left, while on the right, it looks like it's a little bit chopped. And the reason for that is because of oscillations. If oscillations wouldn't be there, the distribution would also show a nice little peak. So the effect is so strong that you can even see it just as these kind of distributions changing behavior by eye directly. So we take that sample, those 2 samples, and we have made an analysis for the known physics to try to extract the oscillation parameters that drive the atmospheric neutrino oscillations. And the 2 parameters are going to be the amplitude of that oscillation, sine square of theta to 3, and the mixing angle, the mass splitting, the phase of that oscillation. And in this plot here, you have the 90% confidence interval, and one of the best fit points for one of the results. For IceCube, these 2 lines are for the 2 event selections. The other lines that show up in this picture, particularly those 3, actually come from T2K- and NOVA experiments that were designed and built in order to measure these oscillations. I highlight this because IceCube DeepCore was not designed and built to measure oscillations. It was an experiment designed and built to measure astrophysical neutrinos. So the fact that we can do this is a little bit striking. I find it very exciting. And the reason is this plot that I was showing you before, that we can look at all of these parameter space, and we can do this in multiple dimensions, and we can use these multiple dimensions to constrain things that we don't know about the detector. And we have these large statistics, huge numbers of events that help us in making very, very statistically significant claims on the effect of oscillations. Now, the another interesting thing is that IceCube DeepCore is the only experiment that sits well above the tau production threshold, which you can maybe see here, which means that we can operate as well in appearance mode, because this analysis that I showed you was only looking for the disappearance of mu neutrinos mainly. But as I was telling you before, most of the mu neutrinos that disappear from here, they have to show up as tau neutrinos. So because we are above the tau production threshold, we can look if that rate of disappearance actually matches to what we expect just from our accepted theory of oscillations. I show you this plot already. One thing that I didn't highlight at the time is that there's actually a component here from tau neutrinos that you can clearly see. It's on this part where you only get back some of the fraction of tau neutrinos because the events look different and we have classified them in tracks and cascades. So we can use those that still remain, and we can try to see how do they compare with the expected number of tau neutrinos that oscillations claim should reappear in your detector. This is something that SuperK and Opera have done. Opera in a very different configuration with only a handful of events, 5, they obtained this result, large uncertainties. SuperK is a little bit too low energy, so it doesn't get to see that many tau neutrinos. These are the results from IceCube analysis A and analysis B for these different samples, depending on whether you look for appearance of only charged current or also charged and neutral currents. The precision is not the best so far, but it's already on the order of 25%, so we can start seeing the appearance of tau neutrinos. Now, on the high energy side, we have a lot more events, and we have a lot more events because we don't demand that the events start in the detector. Events that cross the detector are also accepted. And this sample has been freshly released just a few months back. We have about 300,000 neutrinos in 7 years of data. And these are the distributions of energy and cosine of the zenith angle. And you see that there's very good agreement, even when you have a look at these staggering statistics. Now, we don't expect anything to happen at these high energies because these are well past the interesting oscillation. So what we can do is look for whether there are signatures of something like sterile neutrinos, which is a topic that comes and goes. If you have sterile neutrinos, you have to expand your mixing matrix, including these additional elements, and IceCube would be sensitive to this over here with the mixing of the state 4. And if you only look at one direction for simplicity, what would happen is that you would have some subtle effects at low energies, but you can have these very strong effects at high energies, even if the mixing angle is small. And that's because you have the right interplay of matter effects for some distances and some energies, and you can end up in this resonance condition if sterile neutrinos exist. If you look at the full energy and cosine zenith oscillogram, now the axes are flipped. This is energy, this is cosine zenith. You see that you expect a very strong disappearance and some TeV scale energy. So very different from what I talked about before. So we have looked at this, we have searched for this disappearance, and we have now reported on the results. On the limits that we can place, we still don't see any evidence for sterile neutrinos. This is a mixing angle, this is the mass splitting. And the newest result is this, where everything to the right is ruled out with 99% confidence, and stuff to the left can still be allowed. This already rules out many of the preferred solutions for different tensions that were brought up by experiments like Minibun. We have also extended the analysis to do it as a function of 2 different mixing angles. So independent of the mass splitting, we can also just look at whether the amplitude of oscillations for any of these two elements is there. And we have again excluded a very large region of this space. And the stars here are marking the best fit point just because the feeder has to end up somewhere, but it's not really significant. Now, one more thing that you can do because of oscillations is actually look at the astrophysical neutrinos, because astrophysical neutrinos are really what IceCube was meant to detect, and we have detected some now. So we can ask whether the flavor ratio of these neutrinos actually matches what you would expect. Neutrinos are produced very far away. They shouldn't be immune to oscillations. You should still see oscillations. However, because the source is so far away and it's so extended, this term averages out, and you're really only sensitive to the mixing. The interesting thing is that it doesn't matter what is your starting point for the mixing. With your starting point with the neutrino ratios or your flavor composition at the beginning over here at your source, oscillations make sure that everything gets mixed up and you end up with a ratio very close to 1 to 1 to 1 when you are on Earth, meaning you expect to see roughly the same number of muon, electron, and tau neutrinos on these astrophysical neutrinos. A way to look at it is in this flavor triangle, where you have different components, mu, 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 tau, and you have these lines that show you what is the relative contribution of that flavor to the overall flavor ratio. It doesn't matter if you start with only mu neutrinos at your source. Once you include oscillations, that would move here, which is very close to equal compositions of everything. The same for electron neutrinos. This is the most realistic scenario if you think that cosmic neutrinos come from a similar process as atmospheric neutrinos. You would end up very close to 1 to 1 to 1. So everything should end up in this region over here if physics is what we expect it is, even at these highest energies. And if you were to measure anything in a region different from that, then it would be interesting because you would have to explain that. So IceCube has started looking into this. This is a test of physics over cosmic distances. And you can see here the latest result, the 68% confidence of the best fit point for the flavor composition of these astrophysical neutrinos. The precision is mainly driven by tau neutrinos because they are the hardest ones to see. And there are a couple of IceCube tau candidates which actually made this interesting point right here. But most of the space still allowed. So it would be interesting in the future to see how this evolves and whether we see a flavor ratio of astrophysical neutrinos that is different from what you would expect. Now, all of these are results that we have right now. So what's beyond? For the short term, we're working on a new DeepCore sample. And this is just an example of how that works. This is the rate that we have for our background. This is our starting rate of signal. We're at the moment here with an improved selection that gives us 3 times more events than before. And we have over 2.5 times more lifetime. So we actually expect in the next few months to come up with a measurement that will have a precision, if everything goes right, that would be better than even these dedicated experiments. And this is, again, because of this huge parameter space that we sample and the statistics. So we're very close to this. This is the sensitivity that I'm showing here. It's not a result. We're very close to this. I was hoping to show this at the seminar, but we have some internal review process that is very tough. So we're going through that right now. Another thing that we'll be able to do with the sample is improve a lot our sensitivity for tau neutrino appearance. This is the result. This is what we would expect. It's about a 10% precision if we were to measure exactly one. So after that, what we plan on doing is to actually follow with an upgrade of the detector. In fall 2018, an upgrade for 7 additional strings with further instrumentation to calibrate and reduce the energy threshold of the detector was approved. The deployment is expected in 2022. And the nice thing is that an event that right now is 3 GeV that looks like this on the left would look like this on the right once you have this additional instrumentation. So you can push your energy threshold, but you will also get a lot more information for the events that were on the 20 GeV energy that we already use. Now, let me spend just 1 minute to talk to you about the Global Neutrino Telescope scene, because these are the experiments that are right now. IceCube, the largest one that is operational, and is at the moment upgrading and going towards IceCube Gen 2. Antares is a small scale, it's operational, but it's is going to be decommissioned because the successor is supposed to be KM3net, which is under construction in the Mediterranean Sea. And then on Lake Baikal, you have a Russian experiment, GBD Baikal. Now, these experiments have been planned and being constructed over a long period of time. And the reason is that it's not easy to build things in water. IceCube sacrifices some of its resolution, its precision per event by going to ice, which is a very hard to understand medium. Water would be much easier, but it's very hard to deploy in water. So how about joining some of the IceCube know-how with experts in deep sea deployments? And that's where an interesting possibility comes to Canada, because Canada has this initiative from the University of Victoria called Ocean Networks. And their whole jam is just to deploy things at the bottom of the ocean. So some of us were interested in this and started exploring the possibility. And by now we have deployed a very small scale test setup to understand the optical properties of the water. And you can follow that in the link that I'm providing there, STRAW and STRAW-B. And what we have found is that the optical properties of the water are actually good enough to build something that would detect neutrinos. So we're looking at the possibility of having an actual neutrino observatory off the coast of Canada that would look something like this in the long-term future, the Pacific Ocean Neutrino Explorer, where you could make a really large-scale detector to answer some of these questions about cosmic neutrinos, but you could also search for interesting distortions that would be related to oscillations with very high energy atmospheric neutrinos. Now, let me go back to IceCube, which was really the topic of the talk. So I discussed some high energy searches looking for sterile neutrinos. We still see no evidence. On the low energy side, we have competitive results of standard oscillations leading the new tau appearance results. And in the next few months, we're going to have even better results on that. And we really think we're going to be leading the precision measurements on the atmospheric neutrino side. And the IceCube upgrade, as soon as it comes online, it will just improve everything. Better knowledge of the detector, better precision for the events, lower energy threshold. So it will make for very exciting times to be analyzing this data. So this is where we stand right now. And I hope that I could convince you with this that neutrino telescopes are an exciting tool to study oscillations with great precision. And I'll take any questions if you have. Thank you.
Thank you very much, Juan Pablo. Sorry for the clapping like this. So
that's all right.
Better than nothing. Are there any questions? I think they will be. I don't see any hands raised. Can you go back to slide 58, if you can, please?
Yes, let me just...
I'm not sure if I've been quick enough to check the curve for the improvement with the DeepCore.
Sure. Let me just share that again.
In the plot, in one plot that you showed before, there was a X that I think is the best fit, and it seems that is outside the red curve, or not, maybe.
So we're talking about this.
Yes, the one on the right. Yeah.
Okay, this is a preliminary sensitivity right now. We don't have this result. So this.
Yes, but you showed something before, right?
Yeah. So but this red curve is assuming that the true value lies here in the middle. So we just picked the value and assumed if that would be true, how would the sensitivity look like? Which I think, if I'm not mistaken, we just took one of the global best fits from what is expected. Now, the current results look like this. So right now, the best fit value for IceCube lies at this point, where the X is. So it is not the same point. That's that we have injected for the test.
Okay. Sorry.
Yeah.
Why so?
Just there's really no reason for that. Just
is it so naive? My question is like so stupid. Or?
No. So we could have injected any point within the allowed regions, and we tested one near maximal because if you start testing it outside of maximal, it's a little bit misleading because the space looks very symmetric. So if you test it outside
okay.
maximal, it just starts getting elongated.
Okay, I understand. Thanks.
Yeah.
Are there any other comments or questions? Jeter, go ahead.
Thank you for the talk, Juan Pablo. So my question was, you said that you thought it was fun that IceCube could do this measurement and it wasn't designed for it, which I think is also interesting. Are there many things that you would do differently if you were designing the detector that way? Is it mainly just the energies that you're targeting if you were targeting this science?
So if you're targeting this type of science, there are many things that you could change. So one of them is the design of the sensor. So right now, the sensor does not have uniform acceptance. The PMT sits looking down, as I'm showing here. So if you look only at one region, then light that comes from any other direction has to scatter before it reaches you. So it introduces a lot of complication in the analysis of the data. And this is something that is being changed for the upgrade. So now the sensors are not going to be looking down mostly. It's going to be a combination of sensors that have two PMTs and sensors that have many PMTs looking in all directions. So that's going to make a big difference because right now the detector is intrinsically asymmetric. Another thing is just don't go to ice. Ice is so complicated. It is most of our time is spent understanding what is going on with the Antarctic ice. And it is really clear, which is very nice, but it has a layered structure that is not trivial to understand. And it even has some directions in which the flow of light is preferred just because there is some preferred orientation of the ice crystals. And it has taken 10 years to people studying the detector data to figure these things out. So ice is very convenient because it helps in the deployment and then the stability of the detector. But analyzing the data is really tough. So if you could find a more homogeneous material like water, then those things would be solved. But then you end up with logistical problems that are of a different nature. So, but these two things would improve dramatically the kind of results that you get.
Thank you.
There is another question from Mark. Mark, if you...
Hi, Juan Pablo. Very good talk, thanks. Yeah, so the sterile neutrino search, like slide 53, 54. I mean, neutrino physics community, we want to understand what's going on with the mini boon results, right? And so what do you think the prospects are for IceCube upgrade? And then, will this get it improved, the search? And, what do you think will be the outcome?
So the upgrade introduces more sensors, but it also introduces more calibration devices. So the goal of the upgrade is both to lower the threshold of the detector, but also understand the ice better, which is really, for most of the analysis that we do, the ice is the most complicated thing to understand and to fold into the full analysis. So once more calibration sensors are deployed, we can actually go back and reanalyze all of the data that we have taken because we will have a better understanding of the medium. And this will reduce some of the uncertainties that now drive the precision of these studies. I don't think we're going to get more in statistics because this is already so many events that there's a couple more years is not going to do much. So the goal is going to be try to reanalyze the data once we have a better understanding. And the other thing that is going on right now that I didn't have time to discuss is to have also a combined analysis of the DeepCore and the high energy data, because there are effects. Let me just delete this. So there are effects also at low energies that right now we're not analyzing simultaneously. And the sample that I showed for this result was only through going muons. if we collect a subset of events that actually start in the detector, those would have a much better energy resolution, which can also help. You would have a lot fewer events, but they can be interesting on their own. So all of these things are being pursued, but just following this analysis in the same way is not going to gain you much for statistics. We need the combination of samples, and we're going to need the new information on calibration.
Thank you.
Pierre, please go ahead.
Hello, Juan Pablo. Thank you for the talk. My question was just about your upgrade. How is the quality of the ice that after you basically it refreezes?
Oh, that's a great question. So let me see if I have a little example here, just drawing. Yep. So the short answer is we don't know. This is just a very short sketch of what happens, right? We have to drill the ice with a hot water drill, and then there's water, liquid water in there. We deploy the sensors, and then we let it refreeze on its own. That's what was done for the IceCube deployment. So this borehole ice actually was taken out, it was heated up, there was a lot of gas that went into it, and then you put it back. So we expect a lot of bubbles in that ice. And we have actually seen with some modules that contain a camera, this is one picture of those, that there's a couple of lasers here, and you see that there's a cloudy region, and then it doesn't look as clear anymore. But this changes with time, and in the meantime, the cameras have died because the mounting systems, they don't let them move anymore and things like that. But we know that this ice is one of the largest uncertainties. So right now, we, particularly low energy analysis, basically model every possible configuration of the ice and how that would affect your analysis, and then we just take the hit as an uncertainty. So for the upgrade, there are multiple studies that are gonna try to, what would it take to degas the ice so that we can, the water, sorry, so that we can make sure that there's not that many bubbles when the whole thing refreezes again. And there are more cameras that will be placed to try to study what is going on during the refreezing process, so that even if there is some difference in optical properties, we can model them accurately. But at the moment, this is one of the largest uncertainties. We don't know what happens in this in the vicinity of the domes. Now, the only good thing is that it's not that much of this ice. So the arrival time of photons will be mainly driven by the time that they take enclosed in passing 200 meters of detector. And then this is now on the order of like 10, 20 centimeters, where you expect some additional scattering. But it is one of the biggest problems.
Thank you.
So I don't see any other hands up, so I assume there are no more questions. But Juan Pablo will be happy to answer all the questions if you just send him an email. So,
oh, well, yeah, sure. Feel
so
free.
again, thank you very much, Juan Pablo, for the very nice seminar. And we will reconvene next week, on next Monday, November 9, with the talk on qubits and radioactivity from Laura Cardani from INFN Rome. So thank you very much.
Thank you for having me. Bye.
And enjoy the rest of the day. Ciao, ciao.
Thanks for a great talk.
Ah, oh, he left. I should stop recording.